Hello everyone. In this lecture we are going to discuss about PERT, or Program Evaluation and Review Technique, which is a probabilistic estimation of project duration, unlike critical path method or CPM, where the estimation was quite deterministic. That means we assumed a certain fixed duration for a certain kind of activity, while in reality it may be completed in a shorter duration than what is estimated, and sometimes it may even take longer. So those uncertainties are dealt with in this PERT method. So in probabilistic determination or probabilistic estimation of project duration, the basic understanding is that when an activity is carried out a number of times, suppose the same activity is carried out by different people at different places, then a distribution is obtained. That is, sometimes the activity will be completed in a shorter time, sometimes it will be completed in a longer time, and most of the times it will be completed within in a duration which is between the shortest and longest possible durations. So, and if we find the duration, the distribution, then we'll see that suppose this is the timeline. Generally, we estimate, suppose in deterministic estimates, we'll say that it will be completed within 20 days, but it is found that most of the times it will be around 20 days, but sometimes one or two times it will be taking, suppose, 12 days when everything goes in our favor, and sometimes if things go wrong, it may take even 28 days or 30 days or even 40 days. So if you repeat the activity a lot of times, suppose hundreds of times, then you'll get this kind of a distribution. So as you can see, it may not be always a normal distribution. A normal distribution is which is symmetrical about its mean, but in reality these activities may not be normally distributed, and so therefore we use something called a beta distribution. We don't have to go into too much detail about beta distribution, but only we have to know the fact that unlike normal distribution, which is always symmetrical about its mean, a beta distribution can shift around. The peak may go like this. It may be like a normal distribution. It may be shifting in this direction. Sometimes in some beta distributions, they may be looking like this also. So a beta distribution is quite flexible compared to a normal distribution, which is this unique shape. Now we'll need to sort out some definitions. So we have named these things called optimistic time, pessimistic time, and most likely time. So the optimistic time is the minimum possible time required for completion of an activity or task, and that is expected when everything is going in our favor. That means, suppose if this is the duration, or if this is the distribution of the activity duration, then this lowest time, the shortest time, is called the optimistic time. Let's call it TO. Then pessimistic time is when everything goes wrong, and then it will be when everything goes wrong, even then it will be taking, suppose, these many days or weeks. So this is called TP, or pessimistic time. However, one thing we need to understand is that it excludes the extreme events. That means in extreme event, suppose our estimate varied between 20 to 40 days, while this is suppose 26 days, and the optimistic time is 20 days and the pessimistic time is 40 days. In an extreme event, it may be delayed by a year, but that happens very rarely. So if you want to put a year in this scale, it will be way outside what we can draw in this sheet. So, and the problem is, no matter how many times or how many samples you have here, only one outlier, which is too high, suppose 365 days or maybe 400 days, so that will shift this mean. Although all these values are within 20 to 40 range, only one value of 400 will shift this whole thing, the mean, to somewhere around here, and that's not an actual representative of the nature of the activity, and therefore those extreme events are excluded here. For example, the situation that is happening right now because of the COVID situation, some projects are being delayed by a year, and that is considered an extreme event, and that's why it is not going to be considered in forming this kind of distribution or estimations. Anyway, the most likely time, it is the time taken by an activity in most cases. So based on our definition of central tendency limits, central tendencies, it's by definition the mode of the distribution, that is the value having the highest number of, or the highest frequency, highest number of occurrences. So this is our most likely time, or TM. So this is T optimistic, this is T pessimistic, and this is T most expected, or most expected, or most likely time, not expected. The expected part is we are going to discuss in the next slide. So these are the basic definitions of these time estimates. Now, out of these, if you want to do the calculations, one may think that why don't we simply use the most likely time for estimation, because that's going to be the case for almost all the activities. Whatever is the most likely time, most of the times we are going to get only that duration, and that estimation will be quite accurate. But the problem is that as this distribution is not a normal distribution, and using a beta distribution, it is difficult to use all those statistical tricks to find out the probabilities, and therefore, as we have discussed in our previous lecture, using central tendencies, we are going to find out the mean of this duration, this distribution, and we are going to define that mean as the expected duration of an activity. So expected completion time, it is defined as the mean duration if the activity is carried out a certain number of times. So the distribution for the duration of activity may or may not be normal, but the distribution for the mean will always be normal, as we have learned from central limit theorem. So if the distribution is like this, then the mean will be distributed somewhere around here, and this distribution will be a normal distribution. So that's why this expected completion time is defined as the mean duration. So once we define it as the mean duration, our calculations will become easier, as we'll see in the subsequent slides. But to calculate mean, we have to use some trick, and that is the expected duration, that is the mean of the distribution, is calculated as T expected, or TE, equal to the optimistic time, the pessimistic time, plus 4 times the most likely time divided by 6. And this formula is used because if this is the distribution, then we know that some values are going to be near optimistic time, so we are adding that here. Some values are going to be near the pessimistic time, so we are using that, and most values are going to be near the most likely time, so we are adding 4 times that. That means we are giving a 4 times weightage to the most likely duration and only unit weightage to the optimistic and pessimistic durations or times. Now, why it is 4, why not 3 or 5? I do not have a clear idea. So if you can find somewhere why it is exactly 4 and not 5 or 6 or 3, you can try it and let me know. So it is this formula that you may have to remember, by which we find out the expected duration of an activity. Now let's take an example. So these are the 3 activities, A, B and C. So their optimistic times are 3 days, 5 days and 2 days. Then most likely times are 7, 12 and 5, and pessimistic times were 14, 16 and 10. So if we want to draw the distributions, then they will look like, for A, 3, 7 and 14. So it is skewed to the left. For B, it is 5, 12 and 16. So it will be slightly skewed to the right. And for C, it is 2, 5 and 10. So these are the durations and the expected times based on the formula that we discussed before. It is TE equal to TO plus 4TM plus TP divided by 6. Why divided by 6? Because we have added 6 of the samples, 1 near the optimistic time, 1 near the pessimistic time and 4 near the most likely time. So out of 6, since we have taken 6 samples, so we are dividing again it by 6. So based on that calculation, we will find that the expected durations are 7.5 days, 11.5 days and 5.33 days. Now from this, we should also be able to find out these statistically important terms or parameters, which are the variance and standard deviations. So variance is calculated as this, which is the average sum of square of the errors or deviations. So TE minus TI, if TI is an individual sample, then TE is the mean. So how different something is, a given random sample is, from the mean, that will give us the error or the deviation, that squared because we don't want to cancel out positive and negative, we only want the magnitude of the difference. So, and if we take the total sum and then divide it by the total number of samples, then we'll get the variance. But since it already had the square, to find out the actual variation around the mean, which is called the standard deviation, we take the square root of this variance. However, the problem is that these definitions, although they are the fundamental definitions, will not be able to apply them with our kind of available data, which is only this TP, TO, TP and TM, the extremes and the most likely values. So what we are going to do is that we are going to apply that to the mean, which is normally distributed, and for that we can use an empirical equation or empirical information. That is, if something is normally distributed, now we are dealing with the mean only and not the actual original distribution. So if we have a normal distribution like this, then it is found that empirically that if we have a mean somewhere here then most of the data will be within 3 standard deviations of the from the mean. So one standard deviation is somewhere around here, and it is found to be true for all variables which are normally distributed. So within one normal distribution, this in this direction and one normal distribution in this direction will have approximately 68% of the total data or total population. So if we consider this area, it contains 68% of all the data. Then if we move one more standard deviation here and in this direction, then we will cover some more of the data, and that amounts to 95% of the total observed data. And if we move to 3 standard deviations, this much, then it is found that it contains about 99.7% of all the data. If we move beyond 3 standard deviations, then the only remaining data is 0.3%. So it is quite insignificant, and these are very rare events or rare data or rare samples. So therefore, it is practical to assume that most of the data will be within 3 standard deviations from the mean. So if the standard deviation is this much, then we'll see that the most of the data, 99.7% of the data, will be contained within 6 standard deviations, and therefore these 6 standard deviations are within approximately the TO, that is optimistic time, and the TP, which is the pessimistic time. More precisely, it will be somewhere around here. So this is a practical assumption which is very helpful. Otherwise, we'll have to go for very long tails in both directions, which is not practically possible. And most of the observed data in practical field will be within 3 standard deviations, and therefore the standard within 6 standard deviations, and therefore the standard deviation itself is calculated as this total difference between the extremes divided by 6, and the extremes are pessimistic time and optimistic times. So TP minus TO divided by 6 will give us the standard deviation, and therefore we don't have to go for all these calculations, which is not possible in case of in our case, where these actual values are quite difficult to find. Now that we can find out the standard deviations, in the previous example, we'll add 2 more of these columns. Remember, these variances are also calculated. However, we are not calculating variance first. We are calculating standard deviations from our empirical equation, and then finding out this variance as square of that. But in theory, standard deviation is actually found out after calculating the variance, but here we are doing the opposite, and that is we are finding out the standard deviation first and then finding out the variance. But why do we need the variance? That's another issue. In the final calculations, we do not need it, but for intermediate parts, it is necessary, and that's because while we try to find out the total expected duration, these are only the durations for individual activities A, B, and C. For the total duration, also we'll have to find out the standard deviation. And the problem is that for some of these values, the standard deviation for the total duration is not the sum of the standard deviation by definition, but the variance is. That means the variance associated with the total duration will be equal to the sum of variances of the individual durations, and therefore we are calculating these variances of individual activities in a separate column, which will be useful in the next calculations. So please remember why we are having to calculate the variance as well, because in the final calculations it is not going to be used only for this total duration. The standard deviation of the total duration will have to use this variance. So the total expected duration is calculated as capital TE, which is the sum of the small t or expected durations. But which expected durations? These are only the durations of the critical activities. Suppose if we have a network like this, then if this is the critical part and this is the non-critical part, then we'll have to use the expected durations of the critical part only, the critical activities only, and not the non-critical ones. And the critical path we can determine using the same procedure as the critical path method, as we have already done, using forward and backward paths. The only difference is that the duration of activities will be taken as their respective expected durations and not as a deterministic estimate of a fixed duration for each activity. So other than that, the whole procedure is simply the same. After that, since the expected time for various individual activities are normally distributed, it is assumed that there are some capital TE will also be normally distributed along the critical path. And for the total duration, the standard deviation can be obtained as in this process. The variance we have already calculated for individual activities, which is the standard deviation squared, and so variance for the total duration will be simply sum of those sum of the variances for the critical activities only along the critical path, and then we get the total variance. And this total variance, when we square that, we'll get the standard deviation for the total duration of the project. That means if we have these normal distributions for 3 activities, then their sum will be also a normal distribution by definition. And for that, the standard deviation, which will be approximately this much, will be given by this formula. Now let's go to the example again. So again, we'll assume that all these activities are the critical activities. So we have their optimistic times, most likely times, and pessimistic times, and then we calculated the expected times. Now please note here that although we have calculated expected time separately, it is coming quite close as the most likely time, and that's because the most likely time has a greater impact on calculation of the mean, which is the expected durations, and that's because in the formula itself we gave more weightage to the most likely time, and therefore it will be able to pull that mean closer to itself. Since this was the formula, TO plus 4TM plus TP divided by 6. So therefore these expected durations are quite close to the most likely durations, and therefore the final expected duration of the total project is also very close to the most likely duration of the project. Then in this project, in these columns, what we are doing is we have calculated these variances as square of the standard deviations, and this is the total variance, and this standard deviation is equal to the square root of the total variance, that is this value, and it is not the sum of the individual standard deviations. Please remember this very carefully. As I've mentioned in several places, why, and that is the standard deviation for a total project is not the sum of individual standard deviations, but for the variance that is true, sum of the variance is the same as variance for the total duration. So after that, we can actually use the properties of a normal distribution. So we already assumed that the total duration of the project will be normally distributed, and with the available value of mean, which is what we calculated as capital TE, the expected duration of the project, and standard deviation. Standard deviation gives us how spread out the distribution is. Generally, most of the practical values are spread out up to 3 standard deviations, and beyond that it is quite insignificant. So why we are doing it? It is to answer 2 different types of questions. One is, what is the probability that a project will be completed within a given time? Suppose we have estimated that the project will be completed within 40 days, which is the expected duration, but what is the probability of completing within 35 days, suppose, or in a duration of 45 days. So by definition, the mean duration will have a probability of 50%. That means there is 50% chance that it will be completed within 40 days. But if somebody asks what is the probability of completing it within 35 days, then obviously that probability will be less than 50%, maybe 30% or 20%. And if somebody asks what is the probability that it will be completed within 45 days, then we already know that there is 50% chance that it will be completing within 40 days. If you are giving us 45 days, then we have even greater chance. That means we can say that it is about 75% or 80% or 65% and so on. Another type of question may be, what is the duration of completion having 75% probability or 35% probability and so on. So generally these kind of questions are not asked, but it is a valid question near the extreme. That means what is the duration with 100% probability or 99% probability? So that someone may ask who wants to be very sure. That means they are not concerned about 50%, 75% or 35%, but they are concerned about what is the maximum what is the surety level or certainty level. That means they want to know that no matter what happens, it will be completed within these many days. So for that, we'll have to use this normal distribution table and we'll see how. So a normal distribution table is, the normal distribution itself looks like this. Then by definition, the mean indicates 50% probability. That means, suppose this mean represents 40 days, then our most optimistic estimate was suppose 26 days, and the most pessimistic estimate is, since it is normally distributed, it has to be equally spread out, so it is 54 days. Now if somebody asks what is the probability of completion within 40 days, then we'll have to say that area of this normal distribution curve up to the value 40 is the probability. Then if somebody asks that what is the probability that it will be completed within suppose 45 days, which is, let's say, around here, in that case we already have this 0.5 probability or 50% probability. Along with that, we'll have to add this area as well, which will go up to 45 days. That means this whole area will be giving us the probability. Then if somebody asks what is the probability that it will be completed within 35 days, so which will be somewhere around here, then from 50% we'll have to subtract this portion, and we only are left with this much area, which will be suppose 12% or 15% or something. So that will give us the probability of completion within 35 days. Now these values which are there in this figure, 1, 2, 3 or minus 1, 2, 3 and so on, so these are called the Z values, and what they represent is, it's just the number of standard deviations. The standard deviation is up to Z equal to 1. That means the standard deviation in our case, which we calculated, if I remember correctly, in this table, standard deviation was 2.915. So here this value is 2.915, and let's take our actual example, and our mean was approximately 24.33. So the Z value, also called the standard score or standard normal deviate, is to be determined for any target value. So if somebody asks that what is the probability that it will be completed within 45 days, suppose, or in our case, since it is 24, let's say somebody asks what is the probability of completion within 26 days. So for 26 days, we'll have to calculate the Z value, and Z value means how many standard deviations away a certain value is from the mean. So the mean itself is 24.33. The standard deviation is 2.915. And so how many standard deviations away is 26 from 24.33? So that will be calculated as 26 minus 24.33, that's the actual difference, divided by the standard deviation 2.915, and whatever that will give you, suppose 0.0 0.6 or something. We'll see that later. So it is 0.6 times the standard deviation, or therefore the z value itself is called 0.6. So by definition, if we want to write, the z value is equal to TD minus TE divided by the standard deviation, where TD is the target duration and TE is the expected duration, as we know, and sigma T is the standard deviation for the total duration. Now we have to use this table to find out the area, because here we need to calculate the area. Only in figures we said that we'll have to use this area as the probability, but to find out what the area is, because it's under a curve, so for that we'll have to use a table, which is the standard normal table. So here all these values will give you what is the area and for different values of z. So the table gives us the area under the curve between the mean and the target value. Now the table doesn't give you the total area, and it only gives you the area as shown here, the shaded area or the blue area here. That means it is the area between the mean and the target value. Target means whatever value somebody is asking you. So it can be found from the table based on the z value. So we'll have to first calculate the z value as shown in the previous slide, and when we find out the z value, then from the table we'll have to find out what the area will be. Now remember one thing, that the total area under the curve is unity by definition, and that's why up to mean that means if you see, the half of this will be this half, the first half will be 50%, and the second half will also be 50%, and from this table what we'll get is only this area. So let's see how we can find out the values. The probability of completion within a target duration will be given as 0.5, because we have to add the 50% probability which is up to the mean, and on top of that we have to add the extra probability which is up to our target duration, where A is the area under the curve between the mean and the target duration, which will be given by the table. Now, as we have already said, 0.5 is added because the probability of completion within the expected time or the mean time is already 50%. So whatever value we get from the table, we have to add 0.5 with that value, then only we'll get the resultant probability. Now we'll use the example, our own example, that is this is our expected duration, this is the standard deviation. Variance at this point is not useful anymore. We have already used it to find out the standard deviation. So this is what we are going to use now, only these two values. Now, so somebody is asking you what is the probability of completing the project in 30 days, suppose. So we'll calculate the z value for 30 days. Z value will be, sorry, I calculated it for 28. So let's correct this for 28 days. So for 28 days, how far away is 28 days from our mean 24.33? That is 28 minus 24.33. And how many standard deviations it is away from the mean? For that, we will simply have to divide it by 2.915. So then we'll get the z value as z equal to 1.259 or 1.26 approximately. We are approximating up to the second decimal place because this table only gives us up to the second decimal place. And it is quite comfortable here also because it is 9, so we can very easily approximate it, round off it to 1.26. Now, once we get this value of z, we'll have to use this table, and for this table, we'll see that, you see, this axis gives you the value of z, but this axis also gives you the value of z only at the second decimal place. This vertical axis gives you up to the first decimal place. So our z value is 1.26. So up to 1.2 we'll get from the vertical table, that is this value, 1.2, and for the rest 0.06, this value we'll have to go for the other axis, that means this value. So if we converge them, then we will reach this value, which is 0.3962. So here we'll write that area under the curve is found to be 0.3962. Now, how much area is that? It is only this much area. That is the shaded area, and therefore probability of completion within 28 days will be the probability of completion within 24.33 days plus this extra probability of 0.3962. So that's giving us 89.62% probability that we'll be completing within 28 days. Now, let's take another example. What is the probability of completing within 21 days? That means now we are expecting less than the mean. So the mean duration is 24.33. We are trying to find out what is the probability of completing even before that. So for that, again we'll use the same formula, TD minus TE. In this case, TD is less than TE, and therefore our Z value itself will come as minus, and it is coming as minus 1.14. And similarly, just like the previous problem, we'll go for 1.1 in this table and the rest 0.04 in the horizontal direction. So 1.1 is here and 0.04 is here. So from these we'll converge at this value, that is 0.3729, but we'll have to use this minus sign here because our Z value itself is minus. And therefore, the probability of completion within 21 days is 50%, that is 0.5 minus 0.3729, and that's giving us only 12.7% probability. So, and obviously it was quite clear that it is the probability of completion before the expected duration is obviously less, but in the previous example we saw that probability of completion after the expected date is quite high. Now let's take another example, which is the other type of question, that is, within what duration will the project be completed with a 75% probability. So the client knows what is the dependability level he wants, and he wants to know what is the expected duration for that. So for 75% probability, we'll use 75 is 0.5 plus 0.25. Now 0.5 is up to the mean, and we'll have to only look for 0.25 portion here in the table. So now instead of looking at the axis, we'll have to now look at these values, because the axis will give us only the z values. Now we do not know the z value, we know the area, which is 0.25. So 0.25 will be somewhere around here between these two values, and this is 0.2486 and 0.2517. If I zoom in, as you can see, so in between these two values, that is for this z value and in between these two z values, so for now it is, we can quite comfortably take it as 0.675. From the table, it 0.25 corresponds to a z value of approximately 0.675. So therefore, we know the formula for z. Only thing here is that we do not know the value of z, and now since we found the value of z from the table, so we have put the value of z here. We didn't know the TD, and that was the question, within what duration. So that duration TD we are going to find out, and this is the z value, this is the mean, this is the standard deviation, and from this we found that TD, or the duration within which the project will be completed with 70% probability, is 26.3 days. So this is how we use PERT, or program evaluation and review technique. So you have already seen how different it is from the critical path method. The basic procedures will be same. Only thing is that instead of giving a fixed value of project duration, will give the client a probability, and within that probability we can find out different estimates. So these are the basic differences. I request you to go through different books and other references to find out any other specific differences between these two methods. Thank you.